a few seconds. Okay, there you go. Okay, the recording is started. Okay, so let's start this lecture. Okay, so let me give you the formal welcome to the CSS321 course. Okay, so it's the theory of computability. Okay, so in this week is the first week of this course. So we will basically go through just the course overview. Okay, so it will be hopefully it will be just a class today, and the more intense lecture with more intense content will start from next week. Okay, so in this week, my main point that I would like to make it clear to all of you is that is the rules and all the regulation that we will use in this class, and also the overview content of what you will learn in this course. Okay, so welcome to this lecture, to this course, CSS321. My name is Saran Punyanon. Okay, so I will be the lecturer of this section. Okay, so this course have two sections. Okay, the first one will be taught by Dr. Hung. Okay, and that class will be on Monday, I think in the morning as well. Okay, while the second section, I will be the lecturer, and we will meet every Friday from 9 a.m. to what 12 p.m. Okay, so that will be our lecture time. Okay, it will be every Friday from 9 a.m. to 12 p.m. Okay, so okay, so that I want to okay, so that should be the basic information that you need to know. Oh, one more thing. Okay, another important. Oh, what happened here? I have job to okay. Okay, so another important information is that all the communication on for this course, okay, will be through the Google Classroom. Okay, all the communication will be through the Google Classroom. The lecture notes will be posted on the Google Classroom. The quiz will be posted on the Google Classroom, and the same as the assignment that will be posted on the Google Classroom. Okay, and what else? Okay, and for the lectures, okay, we will use the Google Meet. Okay, and the link to this Google Meet is posted on Google Classroom already. Okay, so we will use this. I believe we will use this link for every week. Hopefully, let me check quickly that it should be the same link. Okay, it should be the same link for every week. Okay, so okay, so next week just join the same link and it should take you to the lecture right away. Okay, so there should be no hiccup like today. Okay, what else? Next, okay, let's go through our agenda then. Okay, I think we have most of the people here already. We have like 52 already. We got like all of us are here. Okay, great. What else? Okay, let's start. Okay, so as I say, okay, today lectures not much content here. Not much content here. Okay, it will be mainly about the administration and then the course overview of what pain you have to go through in this course. Okay, I'm joking. Okay, it will be what do we learn in this course. Okay, the overview of what you will learn in this course, and at the end I will give you a few application that what this course can be applied to. Okay, although mainly the content in this course will be theory. Okay, so it won't be much applications. Okay. Okay, so let's get started. Okay, let's get started from the administration. Okay. Okay, just to emphasize this again for those who arrive a little late. Okay, a little later than others. Let's put it this way. Not officially late, but okay. So For this course, okay, our communication will be through the Google Classroom. Okay, so please make sure that that you have access to the Google Classroom and be able to see what is posted there, and also regularly check what happened in the Google Classroom. Okay, in case I have the announcement to make. Okay, so your responsibility to frequently check the Google Classroom. Okay, for any news or updated. Okay, and to emphasize again, okay, the lecture for this course, CSS 321, section 2, it will be on every Friday from 9 a.m. to 12 p.m. Okay, what else? Okay, so next part should be the part that you are most interested in. Oh, wait, something's wrong. Oh, I think I typed something wrong here. Wait, give me sec. Oh, what's that? Ah, okay. I think I typed something wrong here. Okay, give me a second. Da, 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 da. Okay, syllabus. Dun, dun, dun. Okay, fine. Okay. Okay, totally wrong information. Okay. Sorry about this. It should be assignment. Okay, 30. Okay, that's make more sense. Okay. Sorry for the. Okay, I will up a slide that I uploaded. Okay, there's a wrong number there. I put. Okay, so here's the correct one. Here's the correct one. Okay, so for the grading of this course, okay, your scores will come from these four items. Okay, so the first one will be quizzes. It will be a weekly quizzes. Okay, so every week in the class, okay, let me emphasize this, that the quiz will be given in the class and you have to finish it before the class ends. Okay, so at the end of the class, I will give you something like 20 to 30 minutes, okay, to do the quiz and complete the quiz within the class. Okay, and it will be every week. Every time we have lectures, we will have quiz, including this one. Okay, so that will count as 15% toward your final grade. Okay, so that's the first item. The second item is the weekly assignments. Okay, so for the assignment, you will be given around roughly about 1 week to finish it. Okay, and it will be given every. Oh, okay. So there will be like 12 of the assignments in total that will be given. Okay, so it will be like mostly every week. And for the assignment, okay, it will be given at the end of the class too. Okay, but you have time until next Thursday to finish the assignment for that week. Okay, and that assignment will count as 30% toward your final grade. Okay, and the last two items is just the midterm exam and the final exam, which will be counted as 25% and 30% respectively toward your final grade. Okay, so what else? Okay, and that will be about the grading system of this course. Okay, so the next part that you need to know is about the textbook that we will use for this course. It will be the elements of the theory of computation. Okay, so you should be able to okay, so the content of this course, we will follow this textbook. Okay, so if you want to know more details, then this textbook would be a good resource for you to go to. Okay, so that is a quick overview of the administration. Okay, so but for details, actually, you can find a more detailed version on the Google Classroom. Okay, so let me show you quickly. wait, do I still, okay, I still share the screen. Okay, good. Okay, so please let me know if you have problems hearing me or seeing my screen. Okay, please let me know right away, and then so that I can fix it. Okay, what else? What do I want to show? Okay, what I want to show you next is the more detailed version of the syllabus and also the schedule for the whole course. Okay, so let's go through the syllabus first. Okay, you can find it in the, when you go to the Google Classroom, okay, go to the classwork tab, and then you should see the administration topic. Okay, and inside it, you should see the syllabus and the schedule. Okay, let's start with the syllabus. Okay, so it will give you the details of this course, CSS321 Theory of Computation. Okay, so what else? And this one is for the typo there. Okay, 1/2021. Okay, so Dr. Hong will be the coordinator of this course. Okay, but I will be the lecturer. What else? So in this course, okay, we will study about the different models of the computers and understand relationships between the what we call the computer language, computation, and complexity, and so on. Okay, so the course description can be found here. The grading, okay, as I mentioned earlier, okay, to emphasize again, that the weekly assignment, okay, there will be 12 of them in total, and that will be equal to 30% of your final grade. Okay, so what else? Okay, say attendance checks and quizzes. Okay, actually I will just do quizzes. Okay, I will not do attendance checks. And what else? And that will count toward 50%. So the 15%. Okay. And what else? Okay, oh, the examinations. The examination date is already out. Okay, that's early. Okay, midterm examination will be on the 1st of October between 12 p.m. to 2 p.m. Good time to pick is lunchtime, isn't it? Why do they pick a lunchtime for the midterm exam? Okay, that's strange. Is it normal that they use the like lunchtime for the midterm exam? Can anyone tell me, or is it normal? No, it's not normal, right? Okay, let me check that again, and I will let you know. Maybe there's a type as well. Okay, and for the final exam, okay, right now it's say 3rd of December 2021 from 9 a.m. to 12 p.m. Okay, so for the midterm exam, okay, don't believe it yet. Okay, let me double check it, and I will let you know when I got the answer. Okay. What else? Dun, dun, dun. Okay, so okay, more information that you need to know about these two sections. Okay, so it we will use the same content for lectures. Okay, we will use the same core content for the lectures. Let me emphasize this, that it's just the core content that uh, uh, will be sharing between two sections. Okay, but there will be the extra content that I and Dr. Hu will provide differently. Okay, but please be assured that the main contents of this course we will teach the same. Okay, so the main component, okay, of this course you will learn in both sections. There will be no difference between the two sections. Okay, so don't worry. Whatever section you take, uh, you will have the main basic foundation knowledge, the same foundation knowledge. Okay. Okay, so we will share the same core lecture notes, and also the midterm and the final exams. We will use the same exams for both sections. Okay, and okay, yeah, okay. So we will use the same exams for both sections. Okay, and just to let you know. And what else? However, the assignments, okay, or sometimes the Dr. Hung call it problem sets, okay, and also the quizzes, okay, that will be different. Quizzes and assignments will be different between the two sections, okay, but the exams will be the same. Okay, so what else? You got lax second crop Ajahn. Okay. Okay. It seems that oh, do you mean the screen or what I speak or both? Okay, so I need to wait for 10 seconds to, oh no. Wait, one say both, one say my voice. What is the actual? Okay, so you're talking about 10 seconds between my voice and video, right? Do I understand it correct? So my voice go first and video comes later, or the video, yeah. Oh, it happens every 10 seconds. Your connection is quite bad. Oh no. Oh. Oh. Huh. How do I fix this? It's not like I can improve the internet connection of my computer. It's not something that I can fix by myself. What can I do? It's already connect. It's already give a strong signal. Okay. What how could I do to make it help? If I go slower, will that help, or it doesn't make a difference because it's like 10-second lag. Yeah, 5G starting every couple of seconds. So what? Go for 2.4G. Okay, fine. Let's try that. Let me try that. Okay, go. Okay, I think it's okay. Let's let's try again. Let's try again. Okay. So, is that something that you want me to go over again because of the lag, or is still fine so far? Or is it worse? Okay, just continue. Fine. Okay, let's do that. Okay. Okay. So next, okay, is about the learning material. Already say that. Okay, and for the lecture attendance, okay, you are strongly to encouraged to attend the lectures, okay, and okay, and for this part, okay, I think I would take an advantage of since we are doing the lectures online, so why not record it and pause it so that you can revise it later if needed, okay, rather than force everyone to come to the lectures and do not take advantage of the online lectures and not recording it at all. Okay, so I think that would be a better approach than rather than enforcing this rule. Okay, so I think that would be a better idea in my opinion, and hopefully you share the same idea. Okay, what else? The quizzes, assignment, exams, there will be no makeup for missed work. Okay, so please be aware. Okay, we have the deadline that you have to meet. Okay, but remember this. Okay, if you have the since we are in this COVID-19 situation. Okay, please remember this, that your health is always the first priority. Okay, please take care of your health first. Okay, if you are ill, please don't worry. Okay, let me know. Okay, but please let me know when you are ill and you are about to miss the work, and if you cannot complete the assignment. Okay, please let me know, and okay, and please let me know. Okay, and I will consider cases by cases, but I think most of the time I think I will give you I will allow you to do the makeup work um, to get your grade back. Okay, but it might be different one. Okay, or maybe the same. I will consider it case by case. Okay, but the main point I want you to know here is that please take care of your health first. Okay, your health must be the first priority. Please remember that. And if there are any problems, if there are medical conditions, don't worry about the quiz, the assignment, the exams. Okay, please let me know, and we should be able to figure the way out together. Okay, that is very important here. Okay. Um, okay, what else? Okay, so okay, for the assignment, okay, it will be given, as I say, at the end of the class. So you will have to do it outside of the lecture time. Okay, what else? Ah, okay, so the rules here. Okay, please do it on your own. Okay, do not copy others. Okay, plagiarism is um, what do you call that? A violation, a serious violation that we will not tolerate. Okay, so um, if um, if found, then then the, as you say here, okay, will be punished to the highest degree. Okay, so please um, the quizzes, the assignment, please do it on your own. Plagiarism is not acceptable. Okay, and it is a serious violation. Okay, please do not do that. Okay, what else? Oh, okay. On the Google Classroom, okay, when you submit your work, okay, I believe that when you submit it, sometimes you have to like upload it and also click a submit button. Okay. Uh, oh, okay. And for the quiz, okay, make sure that you complete all the questions, and then make sure that the quiz and also the assignment is completely submit. Okay, please make sure that it is submit properly. Okay, otherwise the Google Classroom will say that you make a late submission. Okay, so please make sure that you submit your work correctly and properly. Okay. Um, okay, what else? Um, okay, so okay, so okay, that's about it. Okay, so that's for the syllabus. That's about it. Is there any questions about it so far? Or we are good? Okay, I think we are good. Let's move on to the schedule then. Okay. Okay, so here is the rough schedule of the content that we will go through in this course. Okay, the timeline may be slightly different, but it should but I mean the overall content should cover all of these topics at the end. Okay, but the timeline might be different, depends on how fast can we go through. It might be slower than we thought. It might be faster than we thought. Okay, but hopefully we should be able to cover. Oh no, we must cover all this content by the end of this course. Okay, we should be able to finish them all without a rush. Okay, so you can look them up on your own. Okay, so but it is given here on the Google Classroom. You can check it on anytime you want. Okay, and what else? Okay, and then the lecture note for this week is already posted here. Okay, there's a slight typo in the grading slide. Okay, I will fix that and upload it again later. Okay. Okay, so to this point, any questions? Okay, if not, okay, then let's move on to the content of this week. Okay, so we'll start off with the course overview. Okay, so let's go. Let's go. Boom. Okay, so that's what is the theory of computation is all about. Okay, so this not just this course, but like this whole branch of computer science, the theory of computation. The main question that they want to answer is this question: what are the fundamental capabilities and limitations of computers? Okay, so before we move on, okay, let me ask you a quick question. Okay, so what if I ask you to measure the limitation or the capabilities of computers? What would you do? What would you uh, I mean, what information would you use to provide this? Do you have any ideas? Anyone still here with me, or is it still 10-second lag that I need to wait until the first answer? Okay, let me paraphrase the questions again. Okay, so the question I'm asking is that if you need to describe the capabilities or limitations of the computers, how would you do it? Okay, that's a good start. Run performance test. Okay, so we are talking about benchmark, right? Benchmark, okay, to see that, hey, with these computers, you run this benchmark, how fast would it go? Okay, thank you very much, Mr. Or wait, is it, I believe, Mr. Leon? Okay, is it like pronounced correctly, Leon? Okay, thank you, Leon. Okay, for the answer. Yes. Okay, great. Okay, so we're talking about benchmark. Good answer. Thank you very much. Okay, that could be one way to talk about this. Okay, it's about the perform. So here we're talking about in terms of performance. How fast could it go? Okay, so if we given them this task to run, how fast could it finish it in how much time, and so on and so on. Okay, that could be one way to look at this. Okay, however, theorists, okay, like computer scientists don't like that. Okay, why? Because what they really want to know is that um, what they want to know about computer is that what they really want to know is that what kind of problems can the computer solve or not. Okay, that is actually the main things that they want to know here, is that if we are given the problems, okay, can we use the computer to solve it or not? Okay, so let's say, for example, let's say that we are given a list of numbers. Can we ask computer to sort it? And I believe that you do a programming course before, so you would know that yes, it is a possible things to do. There are algorithms and functions in programming language to do that. Okay, so that is the solvable problems. And what about other problems like asking your computers to write an article or something like that? Okay, let's say that this is another task. Do you think that computers can do it or not? Okay, so that is a kind of questions that the computer scientists want to answer. Okay, and that is what we mean by the capabilities and the limitations here. Okay, so we are talking about in terms of the problems that the computers can solve and cannot solve. Okay, so it's a different aspect from um, the different aspect from maybe what we normally see. Okay, so it will be toward more theory. Okay, and it will be a lot of proof in this course as a consequence. Okay, so in order to explore the capabilities and limitations of computers in terms of the problems, that it can solve or cannot solve, what do we need to know, and what process um, do we need to take to be able to prove that? Okay, so it turns out that in order to do that, okay, it involves these three components. Okay, let's start with the okay. Let's give the overview of the three first. The first one is the automata. So what is it? So the idea, as I said before, we want to prove the capabilities of and also the limitations of computers. Okay, and when we say about proof stuff, then it involves the mathematics. Okay, so that's why the first step is that we need to describe the computers as the mathematical models. Okay, so that's why we have something called the computational model. Okay, or you can say mathematical models of computation. Okay, so and that will be about that will be what automata is all about, to define, okay, the mathematical models of the computers. And why do we need to do that? So we do that so that we can use this model to define the next part, the computability. Okay, for the computability, the aim or the goal is that we want to classify that the problems that we have, are they solvable or they are not. Okay, um, that it is that's it. Okay, that's the main that's the only thing that we want to know here, that given this task, these problems, can we use computer to solve it or not. Okay, and we will see later that why do we want to know this, why is it matter. Okay, um, when we get to that content. Okay, and the last part is about the complexity. Okay, so complexity is more like the extension of the computability. So let's say that we found the set of problems that are solvable. Okay, then the next question would be, how efficient or how fast can we solve these problems? Ah, okay, so let go back to the my example of sorting numbers. Okay, that sounds like a simple task, isn't it? Just sorting numbers. Okay, so it should be you should be able to write the code to sort a list of numbers in no time. Okay, but what if you're given a task to do something else, like what? Let me think for a second. Okay, maybe something like oh, what should be the thing? Okay, maybe something like, let's say you're given an image, okay, and you need to classify it or identify the objects in the image. Okay, so um, to identify the object in the image. Okay, so with that problem, okay, of the object, that kind of problem is called the object detection. Okay, compared to the sorting number. Okay, you should be able to hopefully you see that these two problems are totally different, and one is seems more difficult than another to write the code to give the answer. Okay, and also the computation time in order to compute the answer, in case that you somehow find the algorithm to solve it. Okay, you should see that also can imagine that one problem will take much more time than another to solve. Okay, so the complexity here is all about try to classify that these problems, okay, is easier than another or not. Okay, so the criteria that we will use to determine that is the okay, is the performance, okay, of the algorithm there. Okay, so we use the performance of the algorithm to determine the complexity here. Okay, that one problem is easy or not depends on the performance of the algorithm. Okay, so we will talk about the performance of algorithm later when we get to this topic. Okay. Okay, so let's go through each one of them more in more details. Okay, so okay, actually let's hide that. Okay, let's go through the each one of them in more details. What do we want to know about them? Okay, so for the complexity, let's start from the complexity theory. Okay, we want to see which problems is hard and which one is easy. Okay, so as I say, we will use the performance of the algorithm, okay, as the criteria. Okay, and in order to measure the performance of the algorithm, it will involve the what we call asymptotic function. Okay, an example of that is the big O notation. Okay, and I think big O notation is the most popular one. Okay, there are also other asymptotic function as well. Okay, but the big O notation will be the how do you say that, the main one here. Okay, and we will use the big O notation um, as the main criteria here. Okay. But however, there are also some problems that we don't know the efficient algorithm yet. Okay, and they are called the NP problems. Okay, those problems are called the NP problems, and we will talk about that when later. Okay, let's not go into details here yet. Okay, let's go into details when we get to that topic. Okay, otherwise this lecture will be very long. Okay, so let's stop it here. Okay, so why? Okay, maybe let's go to the more important questions. Is that why do we need to know about the complexity theory? Okay, why do we need to know this? Why does it matter? Okay, so when to be able to classify the problems as difficult and easy, what the I mean, the usefulness of that is that when you know some problem is difficult and some problem is easy, then what happened is when you design, let's say one day you go and design your system, you try to solve some problems, and then you run into this kind of problems that you know already that they are difficult, then uh, then you know that the task that you have at hand will be difficult. Okay, and um, if it possible, okay, the wise choice for you is to try to alter your problems so that you can avoid those kind of difficult problems and tackle the more easier problem instead. Okay, so that is the benefit of knowing which problem is difficult and which problem is easy. Okay, so that when you design the system, you want to avoid the difficult one and try to use the easy one as many as possible. Okay, and what else? Next, okay, number two, if so this number two is for the NP problems. When you know that these problems have no efficient algorithm, okay, the next best thing you can do is to settle for the less perfect solution. Okay, and that is usually possible. Okay, for the NP problems when they don't have when they say that they don't have the efficient algorithm, they are talking about the perfect solution. Okay, but sometimes you can trade off, okay, for the less uh, not perfect solution, but you get a more efficient algorithm to compute them. Okay, so that is what you can do. Okay, if you run into those kind of um, unsolvable problems like NP problems. Okay, and what else? And for this one, okay, we talk about some problems have a specific characteristics that they are hard only in the worst case situation. Okay, and while they sometimes can be easier and easy most of the time. Okay, and you are unlikely to encounter the worst case situation. Okay, and the complexity theory can help you identify that. Oh, is there any questions? Yes, no, okay. What else? Okay, so number four is actually the extension of number two. Okay, so we are talking about when you cannot find perfect solutions. Sometimes there are other algorithms like randomized computation that can help you find the less than perfect solution, but at least you get an efficient algorithm to compute. Okay, and still give you somewhat a good result. Okay, so that is what complexity theory can help you with. Okay, what else? Okay, and another, oh, actually complexity theory also play a key role in cryptography. Okay, so what does it mean? Okay, we are talking about the encryption and decode and decryption. Okay, so the idea is this: in the cryptography or in the typical encryption and decryption. Okay, so the idea is this: for the encryption, okay, is when you what encoding the your data. Okay, we want that to be a function that is how do you say that is easy. Okay, it should be easy to compute. Okay, it would be an easy function to compute for the encryption. Okay, and you will need, of course, the key to perform the encoding. But on the other hand, for the decoding or for the decryption, okay, it should be a very difficult function to perform if you don't have the key to decrypt it or decoding it. Okay, it should be a very difficult that it becomes invisible for the computer to compute. Okay, so that's the idea. But if you have the key, okay, then it will be easy to decode it and decrypt the data. Okay, so that is the typical idea of the cryptography, and in it, and as you can see, it involves the complexity theory, where they assume that the decoding should be invisible, okay, in terms of the complexity, uh, so that no one could break the encryption without a key. Okay, so that's the complexity theory. Okay, so now let's move on to the computability theory. Okay, sometimes it is known as the recursion theory. And what is it about? It is the area of mathematics to deal with the effective procedure. Okay, so idea is that we want to be able to determine that these problems can be solved by the computers or not, okay, or by the computing device. Uh-huh. And okay, and we don't, and to be able to prove it, we want to prove it in terms of mathematics. Okay. And okay, and then later when we see in this course, okay, we will use some words that will be they might not share the same meaning, okay, but they are equivalent in terms of the computability theory, okay, where we say the word computable, solvable, decidable, and recursive to be considered to be the same here. Okay, and we will see later when we got to that topic why do they share the same meaning. Okay, but for now, okay, let's stop here. What else? Another concept that we should know is about the decidability. Okay, so this is just the term for describing that these problems can be solved algorithmically or not. And what else? And okay, so the decidability is the key point that is the key problems that we want to be able to decide in the computability theory here. Okay, but however, to decide to determine the decidability is very difficult. Okay, so we turn to another technique that can help us determine the decidability quicker, and that technique is called the reducibility. Okay, and the idea of reducibility is that um, this technique try to prove that these two problems have the equivalent difficulty. Okay, and if you can do that, then you can imagine that let's say you start at the beginning, you know that this problem is unsolvable. Okay, let's say problem A, you know that it is unsolvable. Okay, and the idea of reducibility is that if you can prove that two problems have the same difficulty, okay, let's say that I can prove that problems A and problem B share the same difficulty. Combine it with the first information I have is that problem A is unsolvable. Okay, combine these two information together, and what I get is this. What I get is that I can deduce that the problem B is also unsolvable because A and B share the same difficulty, and problem A is also unsolvable. So the problem B must be unsolvable too. So that's the main idea of the reducibility. And with these two concepts combined together, it becomes easier to find a set of problems that are unsolvable and solvable problems. Okay, and what else? Okay, so with that concept, okay, so the problem A that I actually talking about, and is the classic problem that we that is used often in the computability theory is actually this problem. It's called the halting problem. So what is this problem is all about? This problem is just about, let's say you are given the computer code, okay, the computer program. Okay, so what programming language do you know? Java, C++, Python? Pick one. Okay, pick one that you know. Let's say that you're given, your program are given this source code as an input. Okay, and you are asked to write a program to ask whether this program will finish the running or it will continue to run forever. Okay, from as you can see, this problem, it doesn't sound like it will be a difficult one. Okay, but it turns out that to be able to determine this, um, you got into problems. Okay, as you can imagine, to be able, if you think of it, okay, think of a simple solution. To be able to determine that the source code will finish running or not, what would you do? You just simulate it, right? You just run it as it is. Okay, so your code will just run it step by step like a debugger, and just keep running. Okay, so what happened then? Okay, if it finished, then great, it just finished, done. Okay, but if it's not and just run, okay, then you got into the dilemma where you don't know that the given code is still running, and it will finish at some point in the future, or it will just run forever. Okay, you stuck into this dilemma where which one should be the answer. Okay, and at the end you just stuck in the infinite loop, and you will not be able to give the answer. Okay, so that's the problem of the classic halting problem, and that's why it becomes a very the questions sound easy, but it's turned out to be a very difficult problem to solve. Okay, so that will be the problem A that we will use as the to state that it is the unsolvable problems, and then start from there using the reducibility to find other problems that are also unsolvable. Okay, so that's the um, a very simple overview of what the computability theory is all about. Okay, so now to the last part, which is the automata. Okay, so in automata, what we want to do is that we want to describe the computers in terms of mathematics. Okay, and the benefits of doing that is we can use these mathematical models to prove the computabilities and other things that we will see in this course. Okay. But however, as you know, the computers, they comes in different how do you say that, different architectures, different system, and so on. There are so many variation. How would you turn them all into the mathematical model? Okay, and it turns out that you cannot. Okay, you can. It's just too many variation. There are too many. Okay, and each of them require their own mathematical model. Okay, which if you do that, it will make your life very difficult. Okay, so if you think like just naively, just do it. Okay, if, just turn every possible computers architecture and models into mathematics, then you end up with a lot of computational models. Okay, and that with the so many models that it will be very difficult to do anything. So that's why what we do, okay, when we have too many variation, what theorists do is this: we make assumptions. Okay, when there are too many variation, we need to limit that, and to limit that, limit the variation, we make assumptions. Okay, and that's why we create something called the computational model, which is the idealized computers. Okay, so it's a computer model uh, with some specific conditions and also specific assumptions that we made. Okay, so that's why this computational model will be accurate to some level, okay, but not all the way. It won't be the same as the normal computers we know, okay, but it will share some characteristics and okay, it will share some characteristics, and also it will have some features that we want to focus on. Okay, and why do we need to do this? Okay, so as I say earlier, this computational model is created so that we can use them to prove the computability. Okay, so that is the main point of existence of the automata. Okay, so that's why we want to build them that way, that is still somewhat resemblance the conventional computers, but also have the mathematical models that we can use to prove the computability. Okay, so it's like the trade-off between two worlds, the real world and the mathematics world. Okay, so that is what automata is. And what else? Okay, so the example of the automata, there are many variations of them. Okay, even though we make some assumption and make it in idealized computers, we still have a number of possible computational model. Okay, but in this course we will look at only three of them, and they are the three main important one in my opinion. Okay, and that include the finite automaton, push down automaton, and Turing machine. Okay, so this will be the three automata that we will study in this course. Okay, and oh, okay, and do we have time? Okay, if we have time, I will also describe why each one of them is important as well. Okay, maybe later in this lecture. Okay, and actually let's describe it quickly here. Okay, so why these three? Okay, so these three actually they have the different complexity. Okay, these three have different complexity. Okay, while the automaton is the simplest one and the Turing machine is the most complex one. Okay, and what about push down automaton? Okay, the push down automaton is like the last computational model that we still have the efficient algorithm to compute it. Okay, beyond the push down automaton, then we may have the inefficient algorithm to compute them. Okay, so that's why it is important, and the push down automaton also play a key role in the early natural language processing. Okay, and what else? Okay, so basically the finite automaton is the simplest. Okay, the push down automaton have some very interesting properties, and the Turing machine is the most complex one that we will study, and it will show the it pretty much will show you the limitation of the computers. Okay, so that's why we need to look at it as well. Okay. Okay, so if you kind of like sorted the automata based on their complexity, then you should get something that look somewhat like this. Okay, where the lowest one is the simplest one, and if you go up, you get a more complex one. Okay, and what you see here is that you see automata and also grammars. What do they mean? Okay, so let's think about it this way, that this computational model that I just mentioned, the finite automaton, push down automaton, Turing machine, these are like the uh, how do you say this? It's like a function. It's like a computational model. So it's like a function. Okay, so when you talk about function, what else do you need? You need an input, right? You need an input. Okay, so the left side here, the grammar is basically the input of the automata. Okay, so what else? So when you talk about the function, you have the input, and for the input, what else do you need to specify? You need to specify the domain, okay, the set of all possible input, right? Okay, so that is actually what the grammars do here. It provide the possible input uh, of the automata. Okay, so that's why different how do we see this? Different computational model. Okay, the simpler one will accept less number of sorry, let me say this again. Okay, the simpler automata accept the smaller set of have the smaller set of possible input. Okay, while the more complex one usually be able to accept the or be able to understand the input of the simpler one and also the extra one that they have and so on. Okay, so that's how we define the complexity of the automata. Okay, as we study, we will see this in more details. Okay, so let's give you an overview just at this point. Okay, okay, and that's covered the three main parts of the theory of computation. Okay, so here there's a quick note that I would like to mention. Okay, about the quantum computation. Okay, although we want this topic will be out of scope for this course. Okay, but I would like to mention a bit because how do I say that? When it comes into full production, okay, if it become available and popular, then it might change the how we think about the computational model. Okay, so why? Okay, because quantum computers can be think of as a new computational model. Okay, it's different from how we model the conventional computers. Okay, and one thing is about the deterministic. of the computers. In the conventional computers, usually if you given a specific source code with a specific input, then you expect a specific output, okay? And of course, the conventional computers are deterministic, which means that it will just follow the instruction, it just follow the given instructions. And since your input is fixed, your source code is fixed, pretty much everything is fixed. So the output should be fixed as well. Okay, but when it comes to the quantum computation, that is no longer true. Okay, and what happened is that it gives you a new computational model. And what happened is, since as I mentioned earlier, that when we have the automata, let me go back to the okay, as I say earlier, that when we have the automata, oops, wrong button. We have automata to provide the mathematical model to prove the computability. Okay, and what happened is that when the quantum computations is introduced, we have the computational model, and because of that, it makes the earlier proof about the computability. Some of them may change. Okay, so that's why the quantum computation is become very interesting, and everyone is looking at it. Okay, so that is what quantum computation plays a role in this field. Okay, so that's why it can because of its computation is because of its computation power. Okay, it can how do you say that, give the counter example to the previous proof that we have earlier about the conventional machines. Okay, and many things might change in the near future if the quantum computer if there are more research on the quantum computer. Okay, but one thing that is already the quantum computer make a threat, create a threat to the uh, current algorithm. Okay, and one of that is the cryptography. Okay, why is that a problem? A quick overview, a quick summarizes this. Okay, so the conventional cryptography, the current one that we usually use, okay, it is based on the finding the factors of integers. Okay, the current cryptography algorithm, okay, is based on the algorithm for finding integer factors. Okay, which is with this problem is proof already that it is a very difficult problem for the conventional computers. Okay, however, for the quantum computers, there are research that this problem can be solved in an efficient using an efficient algorithm to solve it using quantum computers. Okay, and because of this, okay, it destroy, how do you say it make the assumption that we made earlier false. Okay, and because of that, it could jeopardize the whole crypto system. Okay, so that's why the quantum computers are very interesting topics right now. Okay, so because if you could use the quantum computers to compute the factors of integers quickly, then basically you could use the quantum computers to crack the encryption very quickly as well. Okay, so that what it means here, and you don't want that, right? You don't want someone else to be able to crack your encryption and be able to read your encoding data and so on. Okay, so because of if that happens, then cybersecurity is gone. Then, if that happens. Okay, so that's why the quantum computers is a very interesting topic, and also related to what we will study in this course. However, this part is out of scope and we will not cover it. Okay, so just to point you to see the relationship to other field in the current current landscape of computer science. Okay, so let's move on. Okay, so that's the overview um, of what how do you say that, of what this course is all about. Okay, so we will take a break. Okay, next let's take a break for 10 minutes, and then we will come when we come back we will look at the actual topics that we will cover in this course. Okay, are you good with that? Okay, let's take a 10 minutes break. Okay, right now it's like 17. Okay, let's come back at 10:30. Okay, we will continue at 10:30. Okay, so let's take what is it, 13 minutes, 12 minutes break. Okay, see you in 12 minutes at 10:30. Okay, are you ready? Is everyone back? Yeah. Is anyone here? Mm, okay. Okay. Someone is here. Okay. Let's move on to the second part of this lecture, and then we are done with this lecture. Okay. So this will be a okay last part of the last part of this lecture. Okay. So let's go. Okay, so what will this course will be about? The what content will we learn in this course? Okay, so it will compose of these six. So these six bullets are the core content that we will learn. Okay, so at the beginning, we will start with the fundamental knowledge that you need to know. Okay, so it's a fundamental mathematics that you need to know. Okay, start from sets and relations, functions, okay, and also cover the definition of what language is in terms of mathematics model here. Okay, not language like human language, but the language that the computational model can accept. As I mentioned earlier, that language here means the input, the possible input of the computational machine. Okay, what else? Okay, so the first one is the fundamental. Okay, and second part, we start to look at the finite representation of the languages. Okay, so this will relate it to the finite automaton. Okay, the simplest automata that we will learn. Okay, what else? Okay, so that would be the second part. The third one is the context-free language. Okay, and actually it comes together with the push-down automata. If you remember from the previous diagram, where is it? Where is it? Okay, there you go. Context-free grammar and the push-down automaton are in the same level. What it means is that the push-down automaton is the computational machine model that accepts the context-free grammar. Okay, the context-free grammar is like the possible input of the possible set of input for the push-down automaton. Okay. Okay, what else? Okay, so those two come together in number 3 and 4. And then what else? Number 5, Turing machine is the most complex computational model that we will learn, and it will also set like the boundary of what kind of problems that can be solved efficiently and inefficiently. Okay, so what else? Oh, and the last part is about the computational complexity. Okay, so here we will talk about the asymptotic functions, the big O notation, the NP problems, and their significance. Okay, so that would be in the last part here in the computational complexity. Okay, so that's okay. So this course will talk about these 6 items here. Will be the core content. Okay, that we will learn. Okay, so let's go. Okay, so the learning objective here. What do we want to know? Okay, so um, okay, so after this course, okay, what do we expect? Okay, we expect that you understand the different computational models. Okay, at least the 3 of them that I mentioned earlier: the finite automata, push-down automata, and the Turing machine. Okay, and what else? Okay, another learning objective is that hopefully at the end of this course, you will understand the relationships between different classes of the computational models and also the corresponding languages. Okay, and Okay, what else? And the last part is actually about their applications of these computational models. Okay, in terms of the actually we mentioned about this today in about the how the computational model is related to the compiler design and also and software development environment. How could it be related to? Okay, actually, for software development, we mentioned about it a little bit already about the difficult problems and the easy problems. Um, okay, so what I mean here for the software development is that um, when you have a project to develop a software, okay, you usually break it down into the smaller task, right? You don't want to see the software as the one single entity that you need to solve, but what you want to do is you want to break it down into pieces, and then you delegate your work, these pieces to your teammate, and so that you can work in parallel and finish your software in no time. Okay, so um now the problems comes when you break the problems down into pieces, and then when you try to solve those pieces. Okay, if you run into a difficult problems, then you might have a problems. Okay, so as a good software developers, okay, what you can do is try to modify the flow, and hopefully you will end up with a different set of problems which are easier than the original one. Okay, so that is what you could do for the software development. Okay, but for the compiler design, let's see. Is it next? Okay, we will see next. Okay, what about for the compiler design? What can the computational model helps? Okay, let's see next. Okay, so let's move on to the example applications um, of the what we will learn in this course, the applications of the language and the computational model. Okay, let's see. Okay, I will take, I'll give you two examples. Okay, let's start with the first one, the compiler design, which is more related to the our field. Okay, so let's go. Let's start with the compiler design. Okay, so here in this part, I want you to consider the lexical analysis task of the compiler. Okay, so what is the lexical analysis? Okay, think of it like this. So for the compiler, its main job is what? Its main job is to convert the source code into an executable file, right? Okay, if you think of it as the like Java and C or C++, okay, you need to convert the source code. Okay, so for Java, you have .java, right? You need to convert it into what, like .jar, JAR, or something else. Okay, and for the C or C++ code, okay, you need to convert from the source code into the object and then into an executable file, right? Okay, you know C and C++ or Java, right? Or what programming language do you know? No, or you don't know any programming language? Okay, we mainly studied Java. Good. Okay, okay. If I make reference, I will go toward Java then. Okay, good. Thank you. What else? Thank you, Leon. Okay. Next, okay, so we talk about the lexical analysis here. Okay, so let's say we are given a source code, okay, and let's say it contains this part, this if-else statement. Okay, so um, okay, so here I want you to imagine what happened behind the scene. What happened when the compiler is given the source code? What does it has to do? Okay, so first it have to understand this statement. It have to be able to recognize that this is an if-else statement where you have what? You have the if keyword followed by the condition and then followed by the code block. And then here comes another keyword else. And then to be able to recognize that you don't need the condition now, but you just skip to the code block, skip to another code block right away, and so on. Okay, so that is the lexical analysis is all about. Okay, to be able to convert the source code so that the computers understand it as it should be, as a instructions. Okay, so what does it has to be able to recognize? It has to be able to recognize the keyword. Okay, it has to be able to recognize there's a symbol, the condition. It must be able to recognize the code block and so on. Okay, but as we know, okay, computers program, they see the source code as a string, right? Okay, the source code is just another string. Okay, that all it is to the computer. It's just a list of characters put together into the source code. Okay, so this is what it see. Okay, for the condition, you just see that it is a sequence of characters like this, like if space, then parenthesis, I space greater than equal 0, close parenthesis, and then new line symbol, and so on. Okay, so this is all the compiler see. This is the input for the compiler. Now it must be able to convert this string into what we mentioned earlier, to be able to recognize the keyword like if and else, to be able to recognize the condition, and in the condition it must be able to recognize that, hey, this is a variable, this is constant, and we are comparing this to using this operation and so on, and also be able to recognize the code block that it has to perform as well. Okay, so a lot of things that need to be recognized here. So the problem is, how can it do that? Okay, so we already talked about this, that lexical analysis, that we need to be able to, given the string, classify the words in there and categorize them into the specific rows. Okay, into the like keywords, conditions, code block, and so on. Okay, what else? One way we could do that, okay, is first to find what we call the token class. Okay, is basically the category of words. So it's a set of words with the same category. Okay, so normally there are many token classes. Okay, but the typical token classes are these. Okay, so they are start from the typical token classes, which compose of the set of identifiers, okay, set of keywords, set of integers. Okay, so identifiers, or you can say variables as well. Okay, and also the keywords, it must be able to recognize the keyword, variables, constant. Okay, it can be integer, it can be float. Okay, and also parentheses. Okay, and even the bracket as well. Okay, what else? Okay, so for the lexical analysis, okay, some token class are infinite set. Okay, so here we are talking about like numbers. Okay, numbers, they are infinite sets. You can write infinite number of numbers. Okay, and while some of them are finite, okay, which should be easier to handle, okay, like parentheses and bracket, and also keywords, right? Keywords, they are a fixed number, a fixed size set of keywords here in the programming language. It's not that you can just keep creating new keyword, okay, unless then the new versions come and new keywords is introduced. Okay, which doesn't happen often. Okay, what else? Okay, so that is talk about the token class. Okay, and that's for the set of words. Okay, and okay, so for here, I want you to okay think about the English language for a second here. That to give you another analogy. Okay, not just the programming language, but also the English language can somewhat be related to the automata as well. Okay, and in this case, for the English language and also other language, what you can do is one thing you can do, okay, using the automata is about the part of speech, okay, the part of speech tag, okay, or sometimes we just call it the post tag, okay, is part of speech tells you that for each word in the sentence, okay, what is the role of that word in the sentence? Okay, so for example, let's say what I let's say what do I okay, let's say a sentence say I am awesome. Okay, okay, so you have a noun, or you can say pronoun as I and D, and then you have the verb as am, and then adjective is awesome. Okay, something like this. Okay, so you can classify each word, okay, based on a specific type of what is role in that sentence. Okay, so and what else? And these roles, they have specific patterns. It's not like you can just put them in any order, right? You need to put them in a specific order based on specified by the grammar of that language. Okay, so the same thing here is applied to in the lexical analysis when we compile the the source code. Okay, so that's why the source code has to follow the syntax um, specified by the programming language as well. Okay, and different programming language may have a different syntax because of the same reason here. Okay, like the language, if you do use the English language, then the part of speech, the order of the words based on the part of speech can be different from the Thai language or from the Chinese language and so on. Okay, I mean Chinese language, I mean the Mandarin and so on. Okay, okay, what else? Okay, let's come back to our example, the lexical analysis. Okay, so we have what? We have the informal. Okay, so this is like a simple lexical analysis. Okay, it doesn't cover the whole thing, but just to give you the idea of the difficulty of the task and how would automata help solve this kind of problems. Okay, so first we need to define the token classes. Okay, so we basically define what information that we are interested in the source code. So that including something like the identifier, basically the variable names, right? The string of the letters or digits, okay, and so on. We have the integer, or you can think of as a value, okay, like a numbers, digits, float, string, so on. And then you have the operator like the plus minus sign, the what else, slash, the star, and so on. Okay, and then what else? Then you have the another specific kind of operations for comparison. Okay, or what we call here the relation, like the greater than, less than, greater or equal, equal, and so on. And then what else? You need to know about the keyword. Okay, when you read the source code, you need to know where the keywords are as well, like if, then, else, for, while. Um, Wait, for Java, what do you use? Oh, using? No, that's different language. Ah, I forgot Java. Everything gone. Okay, like class. Okay, I think you have class as well. okay, for defining the class and so on. Okay, what else? For white space, okay, sometimes you need to know the we want to know the white space as well. Okay, like the new line is kind of important. Okay, although we have the semicolon to help us separate the different commands. Okay, but new lines also help for some languages like Python. And what else? Space tab. Okay, that for some language it is important. Okay, what else? Okay, so what else? After we identify the role of each part of the string, okay, into the token. Okay, so let's say that we are somehow able to uh, group them together. Let's say we have this substring. We say that this substring is a token of this class, and so on and so on. Okay, when we got this, okay, we sometimes call this string as a lexeme. Okay, okay. And what else? Okay, so this lexeme is important for us to. I mean, it's a substring that already narrowed down to one specific type of token class, and it can be used to perform um, lexical analysis next. Okay, so what else? Okay, so what next that the lexical analysis have to do? Okay, so the lexical analysis have to after it obtained the token of the token sorry, it obtained the pair of the token class and the substring. Then the next thing it has to do is to convert it into the parser. Okay, so what does it mean? So when you got this pair of token and string, the next part is to understand the, how do you say this? It's like to understand the relationship between the different pair of them. Okay, right now we just kind of classify each part separately, but next we need to parse them and be able to understand the relationship between them. Okay, so to give you like the English analogy, what happened here is this. So for the first step, when you find the token class, it's basically you just find the post tag here. Okay, it's like you identify the post tag of each word. Okay, now the next part that I'm about to talk about is the parser. The parser need to take this this um, this token class or the post tag for the English analogy, okay, and be able to see the relationship, to be able to combine them according to the grammar and so on. Okay, and that is exactly what we are about to do next. So when we are given the pair of the token and string, we need to parse them and be able to see the relationship. So for example, here we have the I greater or equal to 0. Okay, so the first step of the lexical analysis is just identify that I is a variable, greater and equal is just another comparison operation, and 0 is a number, is a constant, is a value. Okay, and now the parser, what it has to do is to be able to see these three parts as one condition. Okay, to be able to recognize this as a condition. That what the parser has to do. Okay, and if you can do that, then now your computer is able to understand the function of different pieces of your code now. Okay, and that is how the um, conventional compiler um, understand your source code. Okay. And for the parser step, actually, this will go into the automata. Okay, and to be more precise, it actually used the push down automata to perform the parser. Okay, so you can use the push down automata to perform the parser to understand the source code as it should be. Okay, so that's where the automaton comes into play. Okay, and okay, so that's it about the lexical analysis. Okay, so do you have any questions so far? Okay, if not, let's move on to the next example then. Okay, the next example is in biology. Okay, so it's a different field, and one of the example that I would like to show you. Oh, something happened. Okay, one example that I would like to show you is what they call the John Conway's game of life. Okay, and sometimes they just call it life. Okay, so there's example here. If you follow this link, it should take you to the website that look like this. Okay, it's just a John Conway's game of life. The is a kind of simulation. Okay, that it has a specific rules and okay, with this they can try to simulate the organism or how the population interact with each other. Okay, let me explain it first, and then we will go into the example. Okay, so what is it all about? Okay, so this John Conway's game of life, okay, is a basic structure, okay, of the two-dimensional cellular automaton. Okay, so the idea is that they want to simulate an organism using this two-dimensional grid, um, and where each cell, I mean each table cell, is actually the cell of the simulated organism. Okay, so that's how they see it as in the John Conway's game of life. Okay, and then what else? And then at each step, okay, so here they talk about like each step in time. Okay, each step in time, or as the organism generate or um, um, kind of like move on. Okay, the each cell they switch on and off depends on the following rules. Okay, so they depends on the state of the cell surrounding it. Okay, and the rules are as follow. Okay, do we have pictures? Let me check. Oh, okay, they're not pictures. Okay, fine. Okay, so how does it work? Okay, in this John Conway's game of life, okay, okay, so this is how it works. Okay, for every cell, okay, they will check that if in the next time step that cell will survive or not. Okay, if they survive, if you just turn on keep that cell as yellow as turn on in the website. Okay, and if let me show you here. Okay, so if the cell is survive, it will be a yellow color. Okay, and if not, it will be the gray color showing that the cell is dead. Okay, and what else? Okay, and then in each time step they will check the surrounding egg cells. Okay, that to determine that the cell in the center will survive or not. Okay, so you basically have three possible options. Okay, so the first option is death. If the cell will die and turn from yellow into gray, if the surrounding of that cell, the count is less than 2. Okay, so which means it's 1 or 0, then the cell will die due to what they call as the underpopulation. Okay, what they call as underpopulation, that cell will die. Okay, or if the surrounding is greater than 3. Okay, so you have like a greater than, okay, so at least 4. Okay, 4 or more, okay, of the cell, the living cell surrounding it, then it will die as well due to what they call the overpopulation. Okay, then the cell will convert from yellow to gray. Okay, for the second one, okay, this is the survival state. It means that the yellow cell will still continue to be the yellow cell in the next time step if only 2 conditions possible. A, if the count is exactly 2. Okay, so the count of the neighbor cell, living cell, is exactly 2, so it will survive. or B, the count is exactly 3 and the current cell is on. Okay. Okay, so 2 or 3, the current cell will survive. Okay, and there will be no change. Okay. And for the last one, the last possible condition is called birth. Okay, this is when the current cell is gray, okay, is dead at the beginning, and in the next step it will turn into yellow, which means alive or giving birth. Okay, if and only there's only one condition here, that if the count is exactly 3, and then the current cell will be switched on in the next time step. Okay, so that's how the game works, and it can be used to simulate all kind of things. Okay, so let's see the example. Okay. Okay, so let's see. Oops, I shouldn't do that. Okay, what else? Okay, so okay, maybe I should make it even slower. How do I make it slower? Wait, give me a second. There should be a speed. Okay. The speed control is outside. Okay, there you go. Let make it very slow. Okay, so it's still so fast. It's too fast. Too fast. Okay, let's say for example this point. Okay, you see that it is. Can you see my cursor, right? Okay, so you see that this yellow cell at the top left, it stands alone. Okay, it has only one neighbor. So in next time step, it will disappear. Okay, this step will disappear. And I believe this gray box in the bottom right, it should turn into yellow in the next time step because it has 3 neighbors and so on. Okay, so let's see. Okay, there you go. Okay, so here it's come up, that one becomes gray, and so on and so on. Okay, so this is kind of this is what the John Conway game of life is all about. So you can simulate all kind of things. Okay, so this is example 1. So it might look simple and nothing much is going on. Okay, but with more complex one. Okay, let me find a maybe a simple one. 1, 2. Okay, okay, let's start with this one. Okay, so if I play 1, 2. Okay, so for this one, okay, all the cells, most of the cells stay constant forever, as you can see, that each cell usually have 2 or 3 neighbors. Okay, so that's why there are no change at all. Okay, except for the cells in the middle. Okay, because all of them have only 3. Like for example, this one, it has 3 neighbors, 1, 2, 3. Okay, or this one have 1, 2, 3. Okay, but for the middle, it has only 1 to 4 neighbors, so that's why they keep keeping come up and go. Okay. Okay, so let's see the each step what happened. Okay, let's say okay, let's stop here. Okay, so here what happened. Okay, so in the next step, this cell will disappear because it has only one neighbor. Okay, while this cell will light up because it has 3 neighbors, 1, 2, 3. Okay, and the same goes for this cell because it has 3 neighbors. Okay, so it will be giving birth. Okay, so that's why you have next time step, you got this 2. Okay, and what else? In the next time step, you should get new cells somewhere. Oh wait, where should it be? Maybe somewhere here, I believe. Okay, because it has exactly 3 neighbors. Okay, there you go. And then what else? And then just disappear. Okay, yeah, okay, and then you got like this loop of 1, 2, 3, and so on. Okay, so you can try play with different one of them by yourself. Okay, there are a number of options, a number of preset of them already that you can play. Okay, and okay, so what is this all about with the automaton? Why is it all about? Okay, so this simulation, as you can see, actually how they implement it. This simulation can be implemented using the finite automata, the simplest one that we will learn in this course. Okay, so we can think of each cell as a single automaton. Okay, and then each one will just check for their state and update it accordingly to the rule of the game. Okay, so that's how the finite automata can be applied here. Okay, they will just check according to the each cell will check the condition based on the rule of the game, and then change the state accordingly in the next time step. Okay, so this is what the finite automata can be applied here. Okay, so you can play more with it in your own time. Okay, so let me show you. Is there? Okay, maybe something like this one. Just kind of move to the left and so on. You can try play with a different one. Okay, and you will see each one. Okay, and okay, you can try play with different one of them and see what happens. Okay, and of this one just like flashing in the middle and so on. Okay, 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 you can check it out on your own. Okay, let's move on then. Okay, so what is this game is all about? Why do we even interesting in this? Okay, it turns out that the game of life is very is simple and concise, and it can actually create a complex pattern. Okay, as you can see previously, the last one I showed, they call it like oh, not this one, the earlier is called, what's it, a spaceship. Okay, a spaceship, and the last one is named what? Oh, the name is just the face. Hmm. Whatever it is. Okay, so you can see that it can be create can be used to create interesting patterns. Okay, and as you can see, the simulation can be done using finite automata. Okay, what else? Okay, so in here, the individual grid cell, okay, or what they consider to be the individual organism in the game of life, okay, can be described using the finite automata. Okay, and what else? Uh, okay, so one thing that I want to show here is that even the basic finite automata, the most simplest one that we will show, that we will learn in a few weeks, okay, we can still you can see that it can be applied together to create, I mean, you can put together um, multiple automata to create a more complex things. Okay, it can be used together to create a more complex system. Okay, so what I want to point out here is that one component is basic doesn't mean that the whole system will be basic as well. Okay, you can put multiple basic things together to create a more complex system. Okay, and that is actually might be a better way for you to in terms of the software development, right? You don't want to handle, I mean, in software development, you don't want to handle difficult tasks. You don't want to be assigning yourself difficult problems to solve, but you want to solve easy one, and hope and you want to be able to use the easy problems to put together and becomes the complex system that you want. Okay, so that's uh, that is the kind of idea that I want you to get from this example. Okay. Okay, so the main content of this week, that's about it. Okay, do you have any questions? No? Okay, so if no questions, then let's move on to the last bit of this week, and then I will let you do the quiz and then assignment and then uh, the assignment later. Okay, so what else? Okay, so in the next week, we'll start looking at sets. Okay, so as I mentioned earlier, we will start off with the fundamental in mathematics. Okay, to give you the foundation before before we before we would go through a more complicated proofs and so on. So we will start with sets. Okay, why do we need to know about sets? And okay, before we move on to the idea of sets, why do we need to use sets in this course? Okay, so at the beginning, I mentioned that we want to be able to define the limitation and the capability of the computers, right? Okay, and one way that we can do that is to define a set of problems that the computers can solve and cannot solve. Okay, so we define the limits that, okay, so we define the limits of the computers based on the problems that they can solve or cannot solve. Okay, so that's why we need to know about sets. Okay, so we will use the set notation to define the um, how to say that the group of problems that we can solve and the group of problems that we cannot solve and so on. Okay, so that's why the concept of set in math is very important for this course. Okay, so that's why we will learn about it in the next week. Okay, but this week I will just give you the definition so that um, um, you can work on the quiz and the assignment for this week. Okay, so let's give you a quick. Hopefully you learn all this in high school already, and if not, maybe earlier in other course. Okay, so this is just a revise a review of sets. Okay, so what is set? Okay, a set is a collection of objects. Okay, so here we use objects because it actually can be anything. Okay, it can be number, it can be another set, it can be list, it can be string, it can be, well, anything you can imagine actually. Okay, so it's a collection of that's why we call it a collection of objects. Okay, and what else? And there are a specific how do you say that? It's a specific set that we use often. Okay, let's put it this way. There are some sets that we use often, like what? So that's why, and because we use it often, that's why we give them a special symbol for this set. Okay. Um, for example, what are they? Okay, so let's start with the first one is the set of integer. We will denote them by this symbol, Z. Okay, what else? And then we have the set of non-negative integer. Okay, sometimes we call them the natural number. Okay, so they are just basically the non-negative number, non-negative integers. So this a set start from what? Zero, right? Zero is considered as non-negative. So we start from 0 to 1 and so on to infinite. Okay, what else? We have the set of truth values, or you can call it Boolean value, which can be denoted by the B symbol, and it has only two possible values, which is true or false. Okay, you can call it 1, 0, true, false, TF, so on. Okay, and what else? Okay, actually another important, the one that we use it often is a set of real number of float. Okay, please don't mind my handwriting, which is quite bad. Okay, Okay, we use symbol R for the set of float. Okay, that is another one that we use often as well. Okay, do I miss something? I think we got all. Okay, those are the set that we use often. Okay, and the last example just give you the idea that the set of a collection of objects. The objects here can be anything. Like for example, here I say the set of students in this classroom. This is also another valid set. Okay, it's okay. You might think that student is not a number. It's not a string. How could you make it a collection? Okay, um, you can still put into a set, okay, and think of the student as the object, okay. Or if you think of in terms of Java, then you can think of it as the instance. Okay, it's just a, let's say you have a class of students and you create an instance and you put that instance in a set. Okay, that could be possible too. Okay, so that what set is about. Okay, what else? Okay, so we see the example, we see the definition of set and example. Next, let's see an operation that we can do with set. Okay, the first operation that you should know about is called the member. Okay, it's the member in here. Okay, so we consider that an item, okay, or sometimes we call the elements, okay, or members of okay, let's say this operation tells you that this item or sometimes the element, it determines whether the item or element is a member of the set or not. Okay, so we use this symbol. Um, I don't know the name of this. Just call it in a member of something like this. Okay, so I don't know what the name of it in the Greek letter, but okay, just remember it is this symbol. Okay, and you can we when we read it, you can just say that it is B in L, or B is a member of L, and so on. Okay, so that's how we pronounce it. Okay, and okay, so how does it work? This operation, it takes on the left side, it has to be an element or an item, okay, while the right side has to be a set. Okay, so with this symbol, it can be read as what I write here. B is an element of set L. Okay, and you can write it like this. Okay, so okay, with this operation, you can check that this element is in this set or not. Okay, and it is a very useful operation, and we will use very often throughout this course. Okay, what else? In a set, okay, one property you need to know about set is that we will ignore the repetition of the elements. Okay, so what does it mean? If you, let's say you have this set, Boolean, okay, you have true, true, false. It is the same as true and false. Okay, what I mean is this, and let me write it down. Let's say I have another set contain true, true, false. It's actually the same. Okay, because we just ignore the repetition. If you have, I have two truths here, then I have two truths. I just ignore one of them. I mean, I just keep one of them, and that's it, and move on. Okay, so we ignore the repetition, and also we ignore the order, which means that set of true false is equal to the set of false true. The order doesn't matter. Okay, repetition doesn't matter, the order doesn't matter. That is what set is about. It just worry about the set is worried only about the collection of objects. You just want to know that what objects is inside the set. That's it. We don't care about the order. If the repetition is there, we ignore it as well. Okay, so that is the, I think that's the key uh okay, key properties and key operation you need to know for this week. Okay. One last thing that you need to know um, for today's lecture, okay, is that the set can be displayed mainly in two ways. Okay, we usually have two ways to display uh, or describe the set. The first one is easy one. Okay, it's the easy way. Is that or you can think of it as a naive way. Basically, you just list all the possible elements in the set. That's it. Okay, so this one is very easy. Okay, and it's very useful when you have a small number of possible. Uh, okay, this one is useful when your set has a small number of members. Okay, if you have a many members, then uh, this way of displaying the set can be painful. Okay, if you have only a handful of members, then this one is a good way to describe the set. Okay, so basically you just listing all the possible elements into the symbol. Okay, with between two brackets, and that's it. Okay, so the example of this is this. For the Boolean set, you just say b equal, so b symbol is the set symbol, and just say the equal sign, then bracket followed by the list of the elements in the set. And in this case, it contains only two members, so that's why I have only two values here. Okay, so that is the first way that we call it the explicitly listing the elements. Okay, but the second way is the more popular one, and we will use it more often when we talk about proof and a more complex system. Okay, we will see this pattern more often. Okay, so the idea is that instead of listing all the possible elements, you just need to specify the properties of the members. That's it. You just need to specify the properties that all the members in the set that share that share properties of the properties that share by all the members in the set. That's it. You specify these share properties, then the reader can infer from these properties to figure out the whole set of the all elements in that set. So you don't need to specify explicitly one by one, but you can just say that, hey, all the values or all the objects that have that have or share these properties, they will be included in this set. That's it. Okay, so that's how it could be done as well. So for example, here, what does it say? So it say that all the what? Okay, so we start with this condition first, that the object in this set must be z, which is the set of integer. So it has to be integer. Okay, first it has to be integer, and what else? So we have the another condition here, and x mod 2 equals 0, which means that uh, the value in this set, it must be modulo by 2, okay, and equals 0. So which means that it must be divisible by 2, right? Okay. Okay, so combine this together, you got the integer that must be divisible by 2, or if you put it into the English word, then you got the set of even integer. That's it. Okay, now you got the set of integer by using this definition. Okay, without having to specify all the even integers possible. Okay. Okay, so that's it. Okay, so there are two ways that you can describe the sets, and there you go. Okay, so to summarize the what we learned in this lecture, okay, so hopefully in this lecture you see the overview of the theory of the computation, that it is mainly that we will that we are about to begin our quest to find it or define the capabilities and limitations of the computers by finding the set of problems that it can solve and cannot solve. Okay, and in order to do that, we will need to explore three main areas, including automata, computability, and the complexity. Okay, so for the automata, we will look at we will look at three popular computational models, including finite automata, push-down automata, and the Turing machine. Okay, and then the computability will comes after we have the definition of the automata. We can use them to prove the computability. Okay, and then the complexity will comes differently, slightly different. Okay, it will be related to the asymptotic functions like big O notation, and with that notation, we can use it to prove the um, oh sorry that and then from there it can be related to the automata, especially the Turing machine, to define the NP class problems or the unsolvable problems. Okay, so that is the what this course is about, and next week we will start our journey with the set. Okay, we will continue where we left off here. Okay, so is there any problem? Sorry, any questions? Okay, is there any questions? Okay, so if there are no questions, I will let you start working on quiz and also the also the assignment as well. Where is it? Okay, so okay, you should see the quiz right now, and you need to finish it by 12 p.m. Okay, so you have like around half an hour to finish it. Okay, and for the problem set 1, okay. Okay, and for the problem set 1, you will be able to start doing it after the class. So after okay, so at 12 p.m. you will be able to start working on the problem set, and you have around 1 week. So the deadline for the problem set 1 is on Thursday, by Thursday before midnight. Okay, so you have to finish it by that time. Okay, so is there any questions about the quiz assignment or anything about this course? Okay, so if we don't have any questions, okay, I will let you do the assignment and a quiz and then assignment later. And okay, so see you next week then. Okay, so that's it for today. That's it for today lectures. Okay, see you next week. Okay, so that's it then. If you don't have any problems, okay, if you have questions, email me or post it on the Google Classroom. Okay, that actually post on the Google Classroom is the preferred way. Okay. Okay, so if there are any problems, let me know. If not, then that's it for today. See you all next week. And I will put the recording on the Google Classroom after I figured out how to do that. Okay, should be soon. Okay, that's it for today. Thank you.